So, in today's tutorial session, we will be discussing problems with respect to how to optimize the drug target interaction as well as prodrugs. So, first question is, explain why morpholine or pyridine is added to a drug molecule. So, in many times what we find is that the drug molecule is actually quite poorly soluble. So, in order to improve the solubility, one needs to add groups which can be hydrophilic in nature, but they are not going to dramatically alter the properties of the drug. So, here nitrogen containing heterocycles such as morpholine or pyridine are quite often used. So, the nitrogen is polar and it definitely increases the polarity, and in some cases the protonated form can also be isolated as water soluble salts. So, here for example, if you connect it through this nitrogen, then you can this whole molecule morpholine is quite polar, and here in the case of pyridine you can make the pyridinium salt and actually isolate it as the pyridinium salt. So, if a polar group is added in order to increase the solubility, it is preferable to add it to the molecule in such a way that it is still exposed to the surrounding water. Okay. So, therefore, because it is exposed to the surrounding water, the drug, when it is bound to the target site, does not have to sort of desolvate before binding to the active site. So, this is an important criterion when we are trying to add more functional groups to the drug. The next question is, CGP 52411 is a useful inhibitor of a protein kinase enzyme. Studies on the structure activity relationship demonstrate that substituents on the aromatic ring such as Cl, Me or OH. So, Cl, Me, OH are bad for activity. Okay. Drug metabolism studies show that para-hydroxylation occurs to produce inactive metabolites. So, how would you modify the structure to protect it from metabolism? Okay. So, here the question is that none of these molecules are useful, and this site is actually susceptible to metabolism. So, we can follow a couple of strategies. The first one is to use a steric shield strategy. So, because this is the position of attack, what we could do is we could add one or two methyl groups around this carbon, and this presents a steric shield for it to be oxidized. Okay. Of course, the problem with this approach is that you are increasing the hydrophobicity of the molecule by adding methyl groups. So, what we could do is we could first add one methyl group in the meta position and see how susceptible it is to oxidation, and then follow it up with a second one if necessary. So, just to recap, steric shield is very useful concept because it helps in preventing chemical and enzymatic degradation. So, for example, esters and amides are particularly prone to hydrolysis. So, by adding a tertiary butyl group here, we can prevent this hydrolysis from occurring. So, here the tertiary butyl group serves as a steric shield. Common strategy that is used to protect such groups is to add steric shields to hinder the approach of the nucleophile. So, these involve addition of bulky groups close to the functional group. The next way to do it would be to replace the hydrogen with a fluorine atom. Okay. So, fluorine is again something that is fairly similar in size to a hydrogen, so it may not affect the size of the molecule by a whole lot. So, this concept is known as a metabolic blocker. So, one of the ways to prevent metabolism or to inhibit metabolism is to use what is known as a metabolic blocker. This we have studied in class. So, the para position here, which X can be replaced by fluorine. So, this molecule which is shown here, which is X equals hydrogen, was actually had excellent anti-cancer activity, but it underwent oxidative metabolism at the para position. So, when the fluoro substituents were successfully added, this molecule actually was quite resistant to metabolism. Another approach is to replace the hydrogen with a deuterium isotope. So, as we know that the deuterium isotope effect may be operational, and that is the carbon deuterium bond is more difficult to break compared to a carbon hydrogen bond, and this may help slow down the metabolism at that position. Next question is, explain the concept of group shift in drug optimization. So, group shift is nothing but replacing or removing a metabolically vulnerable group if it is possible. Okay. And this group concerned is not involved in the important binding interactions with the binding site. But if the group is important, then we will have to use a different strategy. So, first one is to use a prodrug. strategy where you can mask it with a temporary group and then remove it during metabolism. The second one is to shift the vulnerable group within the molecular skeleton. So, here is an example. So, salbutamol, which was introduced in 1969 for the treatment of asthma, is an analog of the neurotransmitter noradrenaline. So, this is salbutamol and this is noradrenaline. Noradrenaline contains a catechol structure which contains two orthophenolic groups. So, one of the problems with this catechol compound is that it is metabolically susceptible to methylation of one of the phenol groups. So, as both the phenol groups are involved in hydrogen bonds at the receptor site, methylation of one of the phenol groups actually disrupts the hydrogen bonding and makes the molecule inactive. So, here is the hydrogen OH which then undergoes methylation, and since this has no interaction, then the problem is that this becomes inactive. Okay. So, this reaction is catalyzed by catechol O-methyl transferase. So, for example, if you now use an analog, this OMe compound, it has been found to have has useful anti-asthmatic activity, but the effect is of short duration because the compound is rapidly metabolized to the methyl ether. Okay. So, if you use this analog, for example, it is quite good, but it is going to be rapidly metabolized. Okay. So, removing the OH or replacing it with a methyl group was also tried, but these also were found to be inactive because of the important hydrogen bonding interaction. So, therefore, we are in a situation wherein we need the hydrogen bonding capability, but we can't sort of put a phenol ring there because it is going to get methylated. So, this problem can be solved by shifting the group. So, what we do is we shift one of the phenol group to make it a benzyl alcohol. Okay. So, once you do this, then you are making the molecule, if you convert a phenol to a benzyl alcohol, then you are making the molecule less susceptible to the metabolic enzyme, but the receptor binding site may still have activity, and thankfully the receptor appears to be quite lenient over the position of hydrogen bonding. And of course, it is interesting to note that the hydroxyethyl group is also acceptable. So, you have CH2CH2OH or CH2OH, both of these are acceptable to the molecule, to the receptor binding site. Okay. But if you add one more carbon, then it does not work. Okay. So, beyond this, if you add 3 carbons between the benzene ring and the alcohol, then it is too large to fit. So, this also suggests to us that there is a binding region within the receptor binding site which has an available volume. Okay. And then this volume is what we need to sort of work around. So, if you are able to find the right molecule or the right functional group which can fit in this volume, then it is possible to develop the metabolically more stable molecule. So, this is an example of a group shift. So, this identifying this volume becomes very important, and knowledge of this volume helps us in making the molecule more metabolically stable. Okay. So, of course, by doing this, we may make the molecule unrecognizable both to the target as well as the metabolic enzyme. So, the key balance that we need to work with is the fact that we should not allow the molecule to be metabolized. At the same time, it should continue to be recognized by the receptors. The next question, celecoxib is a COX-2 inhibitor and contains a methyl substituent on the phenyl ring. It is known that inhibitory activity increases if this methyl substituent is not present. So, if you have this methyl substituent here, if you remove it, it increases the activity, right, or if it is replaced by a chloro. However, neither of these analogues were used clinically. Why not? So, in order to address this question, we can think about what happens if you remove the methyl group. So, if you remove the methyl group, then the compound itself might be active in the real system, but it is actually susceptible to oxidation. So, once you form the hydroxyl group here, then this compound perhaps is not active. Now, if you replace the hydrogen with chlorine, then what we may actually end up doing is we may be increasing the hydrophobicity at that center, and this may actually result in poor bioavailability. Suggest a mechanism by which methenamine is converted to formaldehyde under acidic conditions. Okay. In order to address this, let us go back and look at how this molecule works. So, methenamine is a stable inactive compound when the pH is more than 5. Okay. But in acidic pH, the compound degrades spontaneously to generate formaldehyde. So, the first step perhaps is that it gets protonated over here, and then probably water attacks here and kicks this out. Okay. So, this may be one mechanism by which you generate a formaldehyde like molecule, which then undergoes further decomposition to produce formaldehyde. But the beauty of this molecule is that in the normal pH of the blood, which is 7.4, this passes around pretty much unchanged. But once it reaches the urinary tract where the pH is quite low, that it degrades to generate formaldehyde, which has antibacterial properties. The next question, acetylcholine is a neurotransmitter that is susceptible to chemical and enzymatic hydrolysis. Suggest strategies that could be used to stabilize the ester group of acetylcholine and show the sort of analogues which might have better stability. Okay. So, here is acetylcholine, and this is the bond that is going to be cleaved by esterases. So, in order to improve the stability of this molecule, what we could do is we could make a cyclopropyl ester. We have already looked at it previously, or we can use a tertiary butyl molecule, which is called a pivalyl group, or we could also introduce maybe a slightly longer chain aliphatic molecule with either an aromatic side chain or just an aliphatic side chain. And the last strategy that might be used is to use an alpha beta unsaturated ester.